This is a joint work with Shanghai Jiao University and Alibaba. Unfortunately, the first author is a student. He cannot make it to the conference due to visa issues, so I'm just presenting this paper, but credit should go to him. Here we consider elastic block storage, and this is the architecture taken from Alibaba EBS. But as far as we know, it's also similar to the cloud block storage architectures in other major cloud companies. So the idea is based on a disaggregated architecture. So there are 3 layers here. So the compute nodes will download the virtual images as virtual disks and operate on this virtual disk. And the I/O operations will be done by the block layer, which manages the I/O between compute nodes and also the distributed file system. And distributed file system is where the images are stored. So one key operation in EBS here is image loading. So when users want to create a virtual disk based on the image, it needs to download the images to the compute layer so that they can operate on the images. Now the naive approach is just simply download the entire image before serving the I/O request. But because the virtual disk size is very huge, it will usually take hours to download. So the common approach, at least that is what is being done in Alibaba EBS, is based on lazy loading. So basically, it fetches image data on demand. So if you need that block, you will just retrieve this block directly. This also allows you to do the quick launch. You don't need to download the whole image. You just download the blocks that you need. Here's the idea. So let's say the compute VM want to start the virtual disk. So first of all, it will issue the read, and the EBS layer will go to the storage layer to try to fetch the image. But if the data is not there, then it will notify the object storage backend to pull the images into the storage layer so that the EBS layer now has the image and return the blocks to the compute VM. So image loading is a very important operation. However, from our trace analysis, we find that actually it is susceptible to these slow I/Os. So here we define slow I/O as the I/Os with latency more than 1 second. And also, among many slow I/O events, we find that lazy loading accounts for 40% of them. Now, there are many reasons behind these slow I/Os. It could be due to resource contention. It could be due to some other background jobs. Unfortunately, it's very difficult to mitigate all these root causes. So the only way is to live with that. And also, we find that it's very difficult to get all the images in advance because the majority of this image is what we call the system virtual disk image, which is the image instantiated from the operating systems. And within these system virtual disk images, there will be public images which only contain the operating system and also the applications. But there are also a significant portion of these images are user-defined. That contains the user data. And these images are so diverse that you cannot simply know everything in advance. You probably need to get these images on the fly. So the challenge here is how we tolerate these slow I/Os in the image loading process. So in fact, image loading, this problem could be viewed as the closed stack problem in image loading. And there are many solutions addressing this. Either it's by cache-based, but as I said, the images are so diverse, you can't really get all the images and cache this in the storage layer. So it's not very feasible. And another thing is maybe you use the peer-to-peer approach to let the block nodes coordinate together, just like BitTorrent. You can share the data so that you can improve the cold start performance. But the peer-to-peer approach is also quite expensive, and it's not acceptable in the EBS service. Some approaches will propose new image abstraction to design specifically for fast image loading, but this may not also be practical because in production surface, there are really a lot of traditional legacy images that we have to stick with. So, so here comes our contributions. We proposed ThinkAhead. It's a data-driven image preloading system for EBS, and the design is backed by field trace analysis in production Alibaba EBS. The goal is to address the slow I/O problem, not just for Alibaba EBS, but also hopefully applicable to general EBS services. And we show that we can increase the data block hit rate by 7.2 times and reduce the wait latency by 98.7% compared to lazy loading. And also we make our prototype and traces available so that people can verify our results. So let me give you a brief overview about the traces. So basically we collect the our trace sequence for the first 6 minutes because we focus on the image loading, so we don't need to download the whole trace sequence. We just focus on the first few minutes, that will be good enough. And in total, there will be about 160,000 virtual disks derived from 2,500 images. And we also collect some virtual disk creation metadata so that it helps us later on analyze about the patterns of the among these sequences. And by the way, there are also a lot of open source block traces, but they did not really include the style I/O patterns. So this trace by itself is very unique. So here we highlight some findings here. First of all, reads are dominant. We find that actually for public images, 84.9% will be for reads and 62.3% for user-defined images. And also there will be a diurnal patterns in the VD creation process. So, so for more details about the trace patterns, you can find them in the paper. Now, good thing about our problem is actually the behavior is kind of predictable. So we can leverage this predictability to help us design a better image loading approach. First of all, we find that the access pattern within the same image is highly similar. So I just said that the images are very diverse, so the patterns across the images are very different. But if you look at the same image, actually the access pattern is quite similar. So we find that actually if we try to look at the similarity in terms of the access pattern actually is quite similar. It's based on some similarity metric in here. And the other thing is there's strong spatial locality in image loading. So what that means is when you load the images, usually you only access a few blocks. So that means that you can prefetch them or to just prefetch a small number of blocks, then you can actually improve the image loading performance significantly. Also, we find that there's a large number of historical traces that allow us to do training effectively. So here it shows that for the top 100 images, actually you can have a lot of trace sequences. These images will be used to generate the virtual disk, and we can use these trace sequences to help us to predict what is next sequence. And finally, there's an extra grace period. So there's a time difference between you fetch the I/O and you actually use the block. So that means that you can use this time window to preload the block, and then you use the block directly. So this allows us to implement some nice preloading approach. So we argue that preloading is a promising approach, and here is how we design this and make it applicable for EBS service. So this is the design overview of ThinkAhead. So here is a central system that coordinates the analysis system. So inside the analysis system, there will be the data preprocessing module that tries to analyze the traces and select the subset of traces for the training. And then based on the group of trace sequences, then we try to identify the blocks that should be preloaded. And also we need to address some corner cases where we just don't have enough historical traces. even though it may not be very common, but it still exists. So we need to address this zero-shot prediction to try to retrieve some trace sequences, not directly from the same image, but from some similar images, which we will address them in our design. By the way, this system is deployed at every EBS cluster. So once we design the preloading sequence, we will notify the block layer to retrieve the images from the storage layer. Let me talk about the design here. So first module is dataset preprocessing. The idea is you have many trace sequences associated with the image. So which trace sequences that you should use to do training. Naively, we can just simply use the most recent trace sequence, but we find that actually this is not very accurate. So we want to look at all the trace sequences available and try to identify the subset of trace sequences that are most variable. So first thing here is we need to remove some outlier before the selection because this outlier could be interfering our selection process. So here we pick 0.5%. This number is really from experience, so we use this in here. And then we try to identify different categories for these trace sequences. And within these categories, we want to also address the R reordering because the asset sequence may be reordered for some reasons. So we want to identify the similarity. And here we compute pairwise Pearson correlation coefficient to check if two trace sequences are similar. And the idea of using PCC is, first of all, it's efficient. Second of all, it can address the ordering issue. Finally, we will divide this category into different groups. And so these groups of trace sequences is what we want to do the training. And we also select one centroid within each group so that later on we can monitor whether the actual trace sequence is deviated from this centroid a lot, which implies that it deviated from this group a lot. So now we have this group of trace sequences. The next step is how we use these trace sequences to determine the pooling sequence. Now, one thing I would like to highlight is that we cannot just simply follow the actual order to pool the blocks because actually it may not be efficient. It does not take into account the density. So here is one example. So let's say your asset sequence is 0.0122. So then you may follow this sequence directly. So you preload block 0 and then block 1 and then block 2. However, because of the constrained bandwidth, preloading may take some time. So it will take some time for you to preload block 0 and then block 1 and finally you get block 2. But you'll find that actually block 2 is accessed very frequently. So it would really take a long time until you really see the hits, until block 2 is actually downloaded. So a different approach would be you can preload block 2 first and then block 0 and block 1. Now, when you access block 0 and block 1, you will still see misses. But then when you access block 2 very frequently, then you will get the hits very soon. So these two examples tell us that if you do this reordering, we can reduce the wait latency by a lot compared to the history-based approach that is based on the exact order of the asset sequence. So in this case, we derived we come up with a scheme called the score-based block selection. And the idea is we try to derive a score for each block that takes into account the access count, average access time, and also minimum access time. And so basic idea is higher score means the block should be more preferred to be preloaded. Okay. But you notice that actually the count and also the access time are in two different units. So here we actually use a weighted parameter alpha and beta to include them together. But how do we choose these parameters? So here we need to also address this dynamics in the actual network bandwidth. So the idea is we search for alpha and beta using the genetic algorithm. It's an algorithm that's used to search for the optimal parameters. And then we divide the network bandwidth into bins so that if there's sudden change in terms of the bandwidth, then we run our genetic algorithm. And then also we monitor the trace sequence. And if it's deviated from the centroid, we will switch to another group and use the group of trace sequences to help us do the training. Finally, we need to address the zero shot scenarios. So the idea is we try to identify similar images. So the basic idea is we try to first select the images from the same family, and then also from the same family, same user, and also identify similar metadata. So if you don't have enough historical traces, you will identify similar images and use them to give you the trace sequences to help you do the training. So finally, we do the evaluation. The paper will report a lot of evaluation results, so I highlight two of them in here. First of all is we run in a controlled environment where we use a simulator to run, to compare ThinkAhead with a lot of existing approaches. It's kind of dense in here, but what we show is it can achieve up to 3.8 and 1.8 times higher hit rate than lazy load and history-based approach. History-based approach means that you use the exact order to retrieve the data. So hit rate high means better. And this one is the weight latency, medium weight latency, lower is better. So actually you see that actually it has 0 weight latency when the bandwidth is starting at 6 megabyte per second bandwidth, which means that previous approaches, it still takes some time to preload the data, but for our case, we can preload correctly, and we don't have weight latency for more than half of the cases. And also for the zero shot scenarios, we also get quite good performance. And we also measure the performance in production, and we show that compared with the lazy load approach, it can achieve 5.3 times improvement on slow IOs. So here comes our conclusion. ThinkAhead is a data-driven preloading system for virtual disk images. The main contribution is about the design of how we data-driven design for ThinkAhead for image preloading, and also we have trace analysis to back up our design. So the prototype and traces are available, so feel free to use them for your work. Thank you. I'm happy to take questions and comments.